Hello everyone, welcome to the Bodhi Academy. In today's PYQ series, we are going to solve PYQs of 12th Physics, chapter Semiconductor Electronics, Materials, Devices and Simple Circuits. So let's solve the first question. For a CE common emitter amplifier, the audio signal voltage across the collector resistance of 2K ohms is 2 volts. The current amplification factor beta of the transistor is 100. For the input resistance of 1K ohm, the input signal voltage will be 0.02 volt, 0.1 volt, 0.01 volt or 0.001 volt. So for a CE common amplifier, the audio signal voltage across the collector resistance of 2K is 2 volts. So the current amplification factor beta is 100. For the input signal resistance, the input voltage will be 0.0 volt. So we can mathematically write it as IC equal to VC upon RC. That will be 2 multiplied by 10 raised to 3. So we'll get it as 10 raised to minus 3 amperes. So IB equal to IC upon beta. So that will be 10 raised to minus 3 upon 10 square. So that will be 10 raised to minus 5. So VI equal to IB, RI equal to 10 raised to minus 5 into 10 raised to 3. So that will be 10 raised to minus 2 volts. So that will be 0.01 volts. Coming to the next question, the following figure shows the input waveforms A, B and the output waveform Y of a gate. Identify the gate and draw its logic symbol. So we have input signal A, input signal Y and output signal Y. So A first for the first thing it's 1, B is also 1, so it will be and output is 0. For the second wave, A is 0, B is also 0 and Y is 1. For the third, A is 1, B is 0, so Y is 0. And for the fourth one, A is 0, B is 1, Y is 0. For the last one, A is 1, B is 0 and Y is also 0. From the table, we can identify that the given logic gate is a NOR gate and for this, the symbol is this. Coming to the next question, we have to write the truth table for this combination of logic gate and we have to draw the output Y for this A input and B input. So the combination of logic gate A and B is not AND gate. So for input A 0 and input B 0 will have C1, D1 and Y will be 0. Similarly 0, 1 will give us 1, 0 and finally output will be 1. Similarly for 1, 0 will have C0, D1 and output Y will be 1. A 1, B 1, C will be 0, D will be 0 and Y will be 1. Now for input A1, A0, B0 will have Y also 0. For A1, B1, Y will also be 1. For A0, B0, Y will be 0. For A1, B0, Y will be 1. For A0, B1, Y will be 1. And for A1, B0, Y will be 1. Coming to the next question, a pure semiconductor has equal electron and hole concentrations. On doping with certain impurity, the hole concentration increases. First one, what type of extrinsic semiconductor is obtained on doping? So P-type semiconductor is obtained. And how does the energy gap vary with doping? An acceptor energy level E is formed which lies slightly above the top of the valence bond. Coming to the next question, name the two processes that occur during the formation of a p-n junction. Diffusion of charge carriers occur and development of the potential barriers. Why is the space charge region on either side of the junction called a depletion region? Because it opposes a further diffusion of charge carriers across the junction. That's why it is known as a depletion region. What happens to the width of a depletion region under a forward biased condition and under a reversed biased condition? Under a forward biased condition, the depletion region becomes narrow, and under a reverse bias condition, the width of the depletion region increases. Coming to the next question, write the truth table for a any ND gate. So not AND gate, we have input A0 and input B0. So Y will be 1. Input A1 and input B0, Y will be 1. For input A0 and B1, Y will be 1. And for input A1 and input B1, Y will be 0, because that is the exact opposite of the AND gate. Coming to the next question, with a neat diagram, explain the formation of the depletion region and barrier potential in a PN junction diode, and how does the flow of current through the junction changes during the forward bias condition and for the reverse bias condition. So we have a diagram of showing formation of depletion region and potential barrier in a PN junction diode. The dot represents electrons and the circle represents the hole, and this is the depletion region. So as soon as the PN junction is formed, the charge carriers tend to move from a region of high concentration to a region of low concentration, and thus the electrons from the N region will start to diffuse to the P region, and the holes from the P region will start to diffuse to the N region, and these will get the holes will get neutralized, and similarly the holes from P region will also get neutralized. The P region near the junction is left with immobile negative ions, and the N region near the junction will be left with immobile positive ions as shown in the figure. And this small region at the junction is known as the depletion region, which is depleted of uh, free charge carriers, and it is therefore known as the depletion region. The potential difference across the negative and positive region is called the potential barrier. During the forward bias condition, as the bias voltage increases, the current first increases slowly and then very rapidly, and during the reverse bias condition, the current flow is only due to minority carriers, so it is very low, and beyond a breakdown voltage it increases sharply. Coming to the next question, refer to the given circuit diagram and identify the given circuit. So the circuit diagram shows a full wave rectifier, and which end of the secondary of the transformer should be positive with respect to the center tap to forward bias diode D2. So in order to forward bias diode D2, end B of the transformer should be positive with respect to the center tap. How does the output voltage change if the amplitude of the input voltage is increased? If the amplitude of the input voltage is increased, then the output voltage will also increase. Explain the working of a full wave rectifier with the help of a diagram. So we have a diagram, we have input, we have two diodes D1 and D2, a resistor, and output. A full wave rectifier is an electronic device that converts the entire alternating current into pulsating direct current output. Unlike a half wave rectifier, which uses only one half of the AC cycle, the full wave rectifier utilizes both the positive and negative half of the cycle, making it more efficient. Uh, it can be designed in two ways, using a center tap transformer and or a bridge of four diodes. In the center tap full wave rectifier, a transformer with the center tapped secondary winding and 2 diodes is used, and during the positive half of the AC input, one diode connects with the uh, one diode conducts while the other remains reverse biased, allowing the current to flow through the load. In the negative half cycle, the other diode conducts and a current again flows through the load in the same direction, resulting in the unidirectional DC output. In the bridge rectifier type, the 4 diodes are connected in the bridge configuration, and during the positive half of the cycle, the 2 diodes conduct, allowing current through the load, while during the negative half of the cycle, the other 2 diodes conduct, keeping the direction of the current through the load unchanged. Thus, in both the cases, the output obtained is pulsating DC voltage, and a full wave rectifier has a higher efficiency, provides a greater DC output, and then a half wave rectifier, though the output still contains ripples which can be rectified using a filter capacitor. Coming to the last question, the figure shows the modification of a semiconductor. What type of semiconductor is formed? So from the figure we can make out that it is a pentavalent ion, so it is a n-type semiconductor. How the modification is achieved? Modification is achieved by doping with a pure semiconductor with an atom of group 15, such as silicon or germanium. And what is its effect? So the conductivity of the semiconductor will increase after doping with the group 15 elements, as the majority charge carriers electrons will increase. That's it for today's video. Don't forget to like, share and subscribe to the Bodhi Academy.